Okay, so we're going to be looking at the change in entropy by an adiabatic expansion of a gas. So we want to find our change in entropy delta S. So we're gonna look at a box, and we're gonna suppose that the box has a slit halfway through, and we have some gas that we're gonna label, I'm just gonna call this B for now. So this is gas B, and it's going to eventually expand once I remove this slit, and it's going to cover the entire container. And so we want to find the change in entropy that's associated with this expansion. So let's go through some key terms that we got to know. So the first thing we have to remember is how we defined changes in entropy, specifically for reversible thermodynamic processes. So the way that we can define entropy is in the following way. So we could say some change in entropy, ds, is going to be a change in heat, dq, divided by our temperature. And so, or you could say a change in heat is the temperature times delta S. And so this is very useful. So then we're gonna assume this gas is an ideal gas, in which case we can describe it using the following equation. So using the parameters of the gas, we could say P times V, pressure of gas, times volume of gas, is going to be equal to the number of moles times the gas constant R times the temperature. So now we can see we can relate these terms here. We have temperature here and we have temperature here. So temperature is effectively equal to PV over NR at all times for this ideal gas. So we want to find the total change in entropy, which is going to be our delta S. And so delta S is just going to be an integral of infinitesimally small ds's. And so then we can write, we could solve for that as an integral of heat, of differential changes in heat over our temperature. And then because this is an adiabatic expansion, we can talk about the first law of thermodynamics, which states the change in the energy of a system is equal to the heat that is inserted into the system Q minus the work done by the system, or plus W if it was the work done on the system. But we're going to talk about it using the convention that W represents the work done by the system on the surroundings. So then we can talk about, we can relate this to our differentials. So a differential change in energy is going to equal to differential heat minus differential work. But of course we know this is an adiabatic expansion, so this is just going to equal 0. Therefore, any change in our heat is going to be associated with work done by our system, equivalently there. So we can write this as an integral of dW over T. Okay. Now we can substitute our appropriate variables into our integral. So we're going to write this as NR over PV as follows. NR over PV dW. Now any work associated, we can write work as a function of our parameters. So we know that for expansion, work, any differential work, is just going to equal to P dV. Therefore, when we write this integral, it's going to be an integral of NR over PV times P dV. And so our P's cancel, and we are left with NR. And then we take an integral of 1 over V dV. It's ln of V from V initial to V final. Therefore, when we write this, we can write this as NR ln, and we're going to have V final over V initial. And so then we're going to write that as NR ln2. And so that's the change in entropy associated with this adiabatic expansion, because we are going to say that our V final of this on this container is twice that of our V initial. And so this is going to be the change in entropy associated with that. Now, another question we might want to resolve about this system is, okay, so we know our change in entropy, and we can see it's positive, which is, of course, consistent with our second law of thermodynamics, which states delta S is greater than or equal to 0 for all thermodynamic processes, if you look at the net change in entropy of our universe. But we might want to ask ourselves, okay, what's the associated change in the number of our microstates, omega? And so we have to really go back to the definition of what a microstate even is. So if we look at microstates and entropy and the definitions, we see that entropy is defined as the Boltzmann constant times ln of omega. Okay, and this is our change in our entropy. Our change in our entropy is again going to be nr times the natural logarithm of 2 for our adiabatic expansion. So then we want to say, okay, how is this related to omega? And so we really say, okay, so nr, this nr ln 2 is also equal to k ln times the change in our microstates. Or we could talk about it's going to be our final microstates over our initial microstates. Okay, just like that. And we can raise e to some of these things, and of course some of these things will cancel, so let's try and do that. So we can raise e on both sides. And so what we're going to notice is that we're going to have e to the n r t, and so this is just going to be 2, right? So 2, and then notice we can also relate k as, so nr is really just the number of molecules times k as well. So nr is also equivalent to nk. So we can write this as 2 to the nk, but then k's cancel. So then we're left with 2 to the n equals to the ratio of the number of microstates. And so we see that if we're trying to talk about not entropy, but changes in microstates, changes in the possible configurations, the ways in which we can describe our system, right? Given a certain number of particles, if we adiabatically expand into twice our volume, we are going to increase our number of microstates of our system by a factor 2 to the n, or more generally, if you were to do this with an adiabatic expansion, to say m times the volume, that with n particles, then this would have increased our entropy by a factor m to the n.